Sir, you can start now, sir.
Okay, ma'am. Good evening, students. Today we will be continuing our discussion on alternating current, and I'm going to start my discussion today on different kinds of AC circuits. So I will be sharing my screen with you. Ma'am, can you make me the host of this meeting? Thank you, ma'am. So now I will be sharing the whiteboard with you. So the different kinds of AC circuits we are going to discuss today. The first circuit is AC circuit containing only resistor. Okay, AC circuit containing pure resistor or only resistor. So for that I will be drawing a diagram, circuit diagram. So here you see this is your resistor. Actually, this is your resistor, and here you are having the AC signal. So the AC signal is actually represented by this thing. Okay, AC signal is represented by this kind of sinusoidal wave, and this AC signal is represented by E equal to E naught sin omega t. Okay, and the potential drop across this resistance is given by V equal to IR. So V equal to IR is the potential drop across this resistor. So this is the AC circuit containing pure resistor, and here there won't be any phase difference between the current and the voltage. Okay, because here this circuit contains only resistor. So in this case there won't be any phase difference between the voltage and the current flowing through the circuit, and the equation is given by actually E naught sin omega t equal to IR. So E naught sin omega t equal to I into R. This is the equation, and from this equation we can find out the value of current. So I equal to E naught by R sin omega t, and this E naught by R is otherwise called I naught sin omega t. So here this I naught is called the peak value or the maximum value of current. Okay, peak value or maximum value. So as mentioned by me earlier, there won't be any phase difference between the voltage and the current. So I will be drawing the phasor diagram now. So let us see the phasor diagram. So this is the x and y axis. So this is x and this is y. Here your EMF, okay, and current. That won't be having any phase difference. So both should be marked along the same line. So I will be marking that here. So this line, green color line, represents the EMF, and along this line itself you can find the current also. This is the phasor diagram actually, okay. So this is actually voltage and this is actually current, okay. So this is I naught and this is E naught. So you won't be having any phase difference between voltage and current. So omega t, this is E and this is I, okay. Because from this equation itself you can understand I equal to E naught by R sin omega t. You don't find any phase here, okay. So there is no phase difference between the EMF and current in the phasor diagram. So when there is no phase difference, how does your signals look like, okay. You can see that also. So here your EMF is represented like this, okay, by this dotted line. So this is the EMF. E equal to E naught sin omega t. This green color dotted line. And let us represent the current by solid line. Okay. So this is the current. Of course, it meets here. Okay. So like this, it goes. So this is current. Okay. I equal to I naught sin omega t. There is no phase difference. So the signals actually looks like this. Okay. There is no phase difference. Only the amplitude changes here. Okay. So this is x. Of course, this is y. And now, how will you represent the RMS value here? So here, IRMS, okay? IRMS equal to ERMS divided by R. So this is how you can relate the RMS values of current and voltage, okay? And this is how you need to understand the concept of AC circuit containing pure resistor. So this is the phasor diagram. You won't be having any phase difference between voltage and current. So that's why the signals look like this. And now we are moving on to the next concept, that is AC circuit containing pure inductor. Okay. So AC circuit containing pure inductor. So in this circuit, instead of resistance, you will be having the inductor coil. The inductor coil is actually represented by this symbol. Okay, this is L, and here you will be having the sinusoidal signal represented by this thing, this circle. Okay, so here your EMF is represented by E equal to E naught sin omega t. Okay, now what is the change here? Okay, what is the difference between an AC circuit containing pure resistance and pure inductor? Okay, so when the AC signals pass through the inductor, you will be getting EMF, self-induced EMF in opposite direction to the original EMF. Okay, self-induced EMF. So that is given by E equal to L into di by dt. So nothing but E naught sin omega t equal to L into di by dt. Okay. So once you solve this, you will be getting this equation. I is equal to E naught by omega into L. Okay. Sin within the bracket omega t minus pi by 2. I equal to E naught by omega L sin omega t minus pi by 2. Okay. So in this equation, you can see that there is a phase difference of 90° between the EMF and the current. So from this equation, you can understand that voltage leads the current by a phase angle of pi by 2 or 90°. Okay. From this equation, you can understand that, and the peak value of current is represented by I naught. Okay. So I naught is equal to E naught by omega L. This is the peak value, and from this equation you can understand that the voltage leads current by pi by 2. So in this case, how you can understand the phasor diagram? So let me draw the phasor diagram here. So this is x-axis. Sorry, this is y-axis, and this is x-axis. Okay. So this is actually y. This is x. So here the EMF actually is represented here. The EMF is represented here. So this is E naught, and the angle is actually omega t. Then where is your current? Okay, the current is actually lagging behind. That's the important concept here. The current is actually lagging behind. So you can see here. So this is I naught, and this is actually pi by 2 minus omega t. Okay, pi by 2 minus omega t. That means the entire angle between E naught and I naught here is 90 degrees. So this angle is actually pi by 2 minus omega t. So this is the phasor diagram. You can see the phasors are actually rotating in anti-clockwise direction. So the voltage actually leads current. Okay, voltage is always ahead of this current. Okay, so this thing you can understand from the phasor diagram, and based on this, the signals can be represented by this diagram. So I will represent the signals here. So this is the x and y axis. So E equal to E naught sin omega t is your signal. Okay. So the signal can be represented by sine wave. Okay. This is E equal to E naught sin omega t, sine wave. But your current actually lags, right? The current actually lags behind the voltage, so it can be represented like this. So here can be represented like this. Okay, so this green color line is actually your current. So I equal to I naught sine within the bracket omega t minus pi by 2. So this is the phasor diagram. This is the actual signal diagram, and this is the phasor diagram. And the main thing which you have to keep in mind is that here your EMF leads current by pi by 2. This is the important formula which you need to understand. And of course, we have few more formulas as well. That is the inductive reactance. Okay, inductive reactance represented by the symbol XL. So I will be writing this on this page. Inductive reactance. Inductive reactance is represented by the symbol X suffix L. So what is the meaning of this inductive reactance? So this is the opposition offered by pure inductor. Okay, pure inductor to the flow of AC in the circuit. Just like resistance in a DC circuit, you all might have studied the concept of resistance. So just like that, here in AC circuit, a pure inductor actually offers some opposition to the flow of AC. That is called inductive reactance. And what is the formula for that inductive reactance? That is XL is equal to E naught by I naught. Okay, and we know very well E naught by omega L equal to I naught. That means XL is equal to omega L. Okay, XL is equal to omega L. So here XL equal to E naught by I naught. So this I naught can be taken to the other side, omega L here. So XL equal to omega L. This is the expression for inductive reactance. SI unit is ohm. Okay. and here we have omega is equal to 2 pi f. So omega equal to 2 pi f, where f is the frequency. So using this, your XL is equal to 2 pi into f into L. Okay, XL equal to 2 pi into f into L. So these are the important formulas which you need to keep in mind for AC circuit containing pure inductor. And the other things which you should keep in mind is that for DC, okay, for DC means if the circuit contains direct current, your frequency will be 0 because there is no change in amplitude or direction. So the frequency is 0. So in that case, your XL is also equal to 0. That means inductor gives no opposition to DC. Okay. And the other point is when your frequency tends to infinity, then your XL also tends to infinity. That means when the AC signals change their amplitude and direction very quickly, okay, that is the meaning of this statement. It tends to infinity. So inductor gives high opposition to AC. Okay, so this means inductor blocks. Okay, inductor blocks high frequency AC. So inductor blocks high frequency AC. This is the meaning of this equation. F tends to infinity means XL also tends to infinity. XL means inductive reactance, and inductive reactance tends to infinity. Okay. Do you all understand these two concepts, students? AC circuit containing pure resistor and AC circuit containing pure inductor. Do you all understand this concept?
Yes, sir.
Anyone having any doubts, students?
No, sir.
Okay. If you have any doubt, no issues, you can simply unmute yourself and you can raise your doubt. Okay, raise your queries here, so no problem. Don't hesitate to ask your doubts. And now we will be discussing the next circuit, that is AC circuit containing pure capacitor. Okay, AC circuit containing pure capacitor. So here you will be having only the capacitor. So I will be representing that capacitor like this. And of course, you all know very well the symbol for capacitor. Just two lines. And the AC signal is represented by this symbol. Okay. So this is capacitor represented by the letter C. This signal is represented by E equal to E naught sin omega t. Okay, when you have the pure capacitor alone, what will happen? So how does your equation change? Okay, so I will be giving you the final equation alone. Okay, I am not going in detail into the derivations. That is I equal to I naught sine or I can write like this. Okay, I equal to E naught divided by 1 by omega c, where c is the capacitance value, to sine within the bracket omega t plus pi by 2. I equal to E naught by 1 by omega c sine omega t plus pi by 2. What is the meaning of this? Here actually current leads voltage. Okay, current leads voltage by pi by 2. Exactly the opposite scenario when you compare this one with a pure inductor. Okay, for a pure inductor your voltage leads current by pi by 2, but here current leads voltage by pi by 2. Okay, so here how can you represent the peak value of current? The peak value of current can be represented like this: I naught equal to omega into c into E naught. Now the phasor diagram here changes due to the change in situation. And how does it change? Let us see. Here actually your current, okay, your current actually leads. So the diagram should be like this. The current is represented by this blue color. So I naught. And your EMF can be represented by this thing. So this is EMF. The angle, the total angle between this current and EMF is 90 degree or pi by 2. So this will be omega t. Okay, and this is the phasor diagram for your AC circuit containing pure capacitor. Because here you should understand that the phasors are actually rotating in anti-clockwise direction. So current is leading the voltage by pi by 2. And here the signals, okay, the signal diagram, how does it change? Here also the EMF follows the sinusoidal pattern. So this is EMF E equal to E naught sine omega t. But now the current, okay, the current should reach the maximum first. The current should reach the maximum first when compared to voltage. So it should be represented by this dotted diagram. Okay, like this. So this green color represents the current that is I equal to I naught sine omega t plus pi by 2. So here we are going to introduce the concept of capacitive reactance. Okay, capacitive reactance. Capacitive reactance. What could be the meaning of this capacitive reactance? Can anyone tell me? What could be the meaning of this capacitive reactance? Can anyone tell me, students? What could be the meaning of this capacitive reactance? Yes? Yeah, we have already discussed the inductive reactance, right? From that, you can actually guess this thing, capacitive reactance. Yes, students, you can just make a guess, no issues. Even though if it is wrong, then no issues. You can just make a guess. What could be the meaning of capacitive reactance? It is actually the resistance offered by the capacitor. Okay, the resistance offered by the capacitor to AC. Simple. Resistance or opposition. Okay, opposition is the correct word. So opposition offered by capacitor to the flow of AC. Okay, to the flow of AC. This is called capacitive reactance, and the symbol is X suffix C. So X suffix C is equal to 1 by omega C. This is the equation. Here also the SI unit for this capacitive reactance is ohm. Okay, capacitive reactance is ohm, and omega is equal to 2 pi f. So how does it affect this XC? So X suffix C is equal to 1 divided by 2 pi f into C. So this is the expression for capacitive reactance. Okay, so now we shall discuss the scenario, different scenario, that is for DC. DC means direct current. Your frequency will be 0, obviously. So in this case, if you put 0 in the denominator, what will happen? Anything divided by 0 will be infinity. So when f equal to 0, then your xc equal to infinity. That means a capacitor always offers infinite resistance to DC. Okay, a capacitor offers infinite resistance to DC. This is the important result here. So you should understand this thing. Okay, capacitor always blocks DC, or it offers infinite resistance to DC. And the next condition is when your frequency is infinity. Okay, when your frequency tends to infinity, what will happen to this equation? Here you will be putting infinity, so anything divided by infinity will be 0. So that means xc will be equal to 0. That means when your frequency becomes infinity, So the capacitor gives low opposition. Okay, capacitor gives low opposition to high frequency. Okay, low opposition to high frequency AC. This is the meaning of this. Then the next thing is when you insert a dielectric. Okay, when you insert a dielectric in between the plates of the capacitor, what happens? When you insert a dielectric, your Xc actually decreases because when it is inversely proportional relation, okay, Xc is inversely proportional to C as it is obvious from this equation. So when you insert a dielectric, C increases. When C increases, Xc automatically decreases due to the inverse proportionality relation. Okay. So these are the concepts related to capacitive reactance. Do you all understand this, students? Do you all understand this? Anyone having any doubt?
No, sir, no doubt, sir. Understood, sir.
Okay, okay. Now let us move on. Okay, now let us move on to the other concepts, that is resistor and inductor in series. RL circuit, that is called RL circuit. RL means resistor and inductor in series. So let me draw the circuit diagram. It is quite similar to pure inductive circuit. The only difference is you introduce a resistance. Okay. So here you are having some resistance, that is R. So this is the inductor coil L, and you will be having the sinusoidal signal here, represented by this symbol E equal to E naught sin omega t. This is your circuit, and you will be having potential drops across this resistance and this inductance. Okay, the potential drop across this resistance is given by V suffix R is equal to V into I naught. Okay, actually I naught into R. So let me draw the phasor diagram. So for this RL circuit, let me draw the phasor diagram. So here you have this resistance and inductor connected in series. So in this case, current flowing through both these elements will be same, because in series combination, okay, current flowing through different elements is always the same. That's the basic concept. So at any instant of time, current flowing through both the resistor and inductor is same. Okay. So here I naught is the peak value of current as usual. Okay, I naught is the peak value of current. That is as usual. Okay, let me correct it here. This is I E equal to E naught sine omega t. So VL and VR. Okay, VL and VR are the potential drop across L and R. So here the potential drop across this inductor is VL, and the potential drop across this resistor is VR. Okay. So now we know very well how we can represent the potential drop. So VR, V suffix R is equal to I naught into R. According to Ohm's law, the potential drop across this resistance is I naught into R, and the potential drop across the inductor is I naught into XL. Okay. So Ohm's law we are using here across the inductor coil. Instead of resistance, we need to use inductive reactance XL. Okay. So here this VR, potential drop across the resistance V, that is VR, the potential drop and this EMF are in phase. Okay, because we know very well when you have a resistance, it doesn't introduce any phase difference between the voltage and current. So this VR and this EMF, okay, both are in phase. But this VL actually leads the current by pi by 2. Okay, I think you can understand this. This VR and EMF both are in phase. So that means here we have VR. Okay, and I will be drawing the E naught here. So here I am having E naught. Okay, but VR and I naught are in phase. So that means when you have your I naught along x-axis, when you have your I naught along x-axis, your VR is also along x-axis. Okay, because VR and I naught are in phase. But we know very well VL. This VL actually leads current by pi by 2. That means this VL can be represented along this direction. Okay, so we have VL here. This is Y, this is X. And this point can be represented as R. And this point can be represented as Q. And this point is O. And the phase difference is phi. Okay. So now we should calculate OR from this diagram. So the OR, actually OR squared is equal to OP squared plus, so this point is P. Okay, OP squared plus OQ squared. Okay, this is a right angle triangle. So OR squared is equal to OP squared plus OQ squared. So this OR, when you want to find out, you need to take the square root of OP square plus OQ square. That means this OR is nothing but E naught. E naught is equal to square root of OP. OP is nothing but VR. Okay. VR square plus OQ is nothing but BL square. So from this, I am continuing here. E naught is equal to root of VR can be written as I into R, okay, like that, I naught into R. So here, I naught into R, the whole square, plus BL means I naught into XL, the whole square. So among both these things, you can take I naught as common. So within the square root, R squared plus XL squared, you will be getting for E naught. Okay, E naught equal to I naught into root of R squared plus XL squared. So here I need to calculate the value of I naught. So I naught is equal to E naught divided by square root of R squared plus XL squared. Okay. So instead of XL, you can write omega L squared. So that is E naught divided by root of R squared plus omega L squared. Instead of XL, I am writing omega L. And this is phi. I need to find out tan phi. Okay, tan phi is equal to VL by VR. So tan phi is equal to VL by VR. VL can be written as I naught XL divided by VR is I naught R. So when you simplify both of them, you will be getting XL by R. Okay. So from this, tan phi can be represented as omega L divided by R. This is tan phi. Okay. This is tan phi equal to omega L divided by R. From this, you can find out phi equal to tan inverse omega L by R. So here you have both a resistance and an inductor coil. So both these elements will offer some resistance to the flow of AC here. So the collective resistance, okay, the collective resistance here is called impedance. Impedance is a term which we will be using frequently when you have more than one kind of element like this. Here you have both R and L, okay. So here we should give the name inductive impedance. So this impedance is a word which you will use when you have more than one element, okay, in the AC circuit. Here you have both resistor and inductor, that is more than one element. So you should use the word impedance. Impedance is the collective opposition offered by all the elements present in the AC circuit to the flow of AC. So here inductive impedance means opposition offered, okay, opposition offered by RL series, inductor and resistance in series to AC. That is called inductive impedance, and that is represented by Z suffix L is equal to E naught by I naught. Okay. So this implies I naught is equal to E naught by ZL. Okay. ZL is nothing but square root of R squared plus XL squared. So ZL equal to square root of R squared plus XL square, otherwise called E naught by I naught. Okay, E naught by I naught is equal to square root of R square plus omega square L square, because XL is equal to omega L, so that is square root of R square plus omega square L square. Okay, so here this is called Z suffix L, inductive impedance. So we know very well omega equal to 2 pi into F. So here instead of omega you should substitute 2 pi F. That means when you square it you will be getting 4 pi squared F square. So in that case Z is equal to or ZL is equal to square root of R square plus, instead of omega, 2 pi F. So that will give you 4 pi squared F squared into L square. This is ZL. ZL equal to square root of R squared plus 4 pi squared F squared L square. This is called impedance, and the reciprocal of impedance is called admittance. The reciprocal of this impedance is called admittance, and that admittance can be represented like this. Admittance is equal to Y is equal to 1 by Z. So that is 1 divided by square root of R square plus omega square L square. That is called admittance. And now we can represent the impedance by impedance triangle. Okay, impedance triangle. So let me explain you what is meant by impedance triangle. So for that I will be drawing this diagram. So here this hypotenuse is called ZL or inductive impedance. Okay. This is called ZL. And the y-axis it is XL, right? So this is R. We will be having the phi here. Okay. So this is called impedance triangle. Do you all understand this concept, students? Inductive impedance and RL circuit. Do you all understand this? Any doubt you have? Yes, students, any doubt you have?
No,
Yes?
sir.
Okay. Are you all revising the concepts periodically or regularly? Are you all revising the concepts? Whatever is discussed in the class? Are you all revising regularly?
Yes, sir.
Okay. Then I will be asking you one question now. Okay. What is the value of resistance offered by a capacitor to DC? What is the value of resistance offered by a capacitor to DC? Can anyone tell me what is the value of resistance offered by a capacitance to DC? Capacitor to DC. What is the value of resistance? We have discussed a few minutes ago, right? I am asking question from that concept only. The concept which we have discussed a few minutes ago. What is the value of resistance offered by a capacitor to DC? Few minutes ago only we discussed, right? So you should be able to answer this question. What is the value of resistance offered by capacitor to DC? Can anyone recollect that and tell me the answer? The value of resistance offered by capacitor to DC. What is the value? Can anyone tell me? Nobody? It is actually infinite. Okay. The capacitor offers infinite resistance to DC. We have discussed that a few minutes ago only. Okay, that's why I asked you this question. So what is the meaning or what is the term you use for the opposition offered by a capacitor to AC? Can you answer this question? The opposition offered by a capacitor to AC is called. What is the term you use for this? The opposition offered by capacitor to AC is called. What is the term? What do you call that? It is actually called capacitive reactance. Okay. So please remember the concepts. Okay. Please don't forget whatever is discussed in the class. Then only you will be getting the full benefits out of these sessions. Okay. You should observe the sessions carefully. You should remember everything. Okay. So the concepts you should remember. Then only you will be able to solve numerical problems. Now we shall keep it this much in this class. We shall continue our discussion on alternating current in our next class also. Thank you so much for joining the session.